Good morning and welcome, everybody. I hope you are all excited for our Astrodynamics event today. You guys are in for an amazing event for the whole day. We have Mr. Milton Davis, who's going to be leading you the whole day, straight here from NASA. So, you guys are very, very fortunate to have him here. But I just want to say we are so excited to be here. Milton is going to start us off with our introduction, and then we're going to just get this whole day rolling. I hope you guys are ready to blast off for our space event today.
Oh, thank you so much, Monica. And I love it. Ready to blast off. We are ready to blast off. Welcome to space, right? It's mystical, it's magical, it's scientific. I'm just so excited about this. Let's get going. Welcome to our space day. You're going to build some rockets today. I'm excited about it. This is called astrodynamics because what you're going to do is we've given you a mission, but no mission can happen without the development of a really cool rocket that can, like Monica said, launch us off into the stratosphere, man. Get us out there and going. We want this satellite that you have going all the way to the moon, to Mars, and beyond. But before we start this lab, I want to engage you all a little bit in a Slido poll. So let's say you're an astronaut. Guess what? We have an astronaut coming to speak to you all today, later on at 1 p.m. Eastern. So if you're here now, we want you to come back. We got an astronaut, but let's say you are an astronaut and you wanted to take one food into space. You're on Mars. You're just hanging out. You're getting hungry. You're looking at the aliens walk by. You're getting, no, I'm just joking. Mac and cheese is coming in there. Mac and cheese. My wife, Constance, makes a mean mac and cheese. She uses Velveeta and cheddar and American. She mixes it all up. Ooh, I love some mozzarella sticks. Got a little burrito bowl. We're going to Chipotle, Monica. A little ice cream, the frozen ice cream. Yeah, this is great stuff,
I
man.
think I
Yeah.
know what you're
I
taking
can,
up there, Milton.
what am I taking?
Giando's Pizza.
That you know it. Giordano's. We are rolling. And for my snack, peanut butter and jelly. You can't beat some peanut butter and jelly. Monica knows me too well. Oh, this is great engagement. I want to give a huge shout out to the developers of this lab. Don't focus on me. Travis had a big part on it, but these students, Lauren and Katie, outstanding job. This lab material that's in here, you're going to love it. They did an outstanding job developing this lab. So I want to give you a little background as well. Why am I here? Why are we talking? Well, this is my journey into space. It started with an RC car. I'm racing these RC cars up and down the street. I'm changing the gears and I'm loving TOEs. I'm a huge space geek. I'm into theories of everything. And we'll talk about that today. How did this entire universe come into existence? We're going to answer a lot of different questions about space. But I didn't really go to a high school that had a lot of technology, but I was blessed. Even though I went to a community college, my counselor really helped me navigate my career path. We'll talk about career paths as well in the wrap up. And because of my love for engineering, which is RC cars and all things theories of everything, which is space, I landed on aerospace. And I've been working at NASA since 2001. That shows my age. I went to Purdue. Shout out to my Boilermakers. I think Betsy went to Purdue as well. Shout out to Betsy, outstanding aerospace engineer, and she's rocking with us today. And this is me as an intern a very, very long time ago. What do I do? I'm trying to answer the question, what are we doing with all these satellites that are dead, right? Let me show you this mission. It's called OSAM-1. And what's happening with OSAM-1 is we're going to take satellites like this one, like you see in orange. It's just sitting there. It's run out of gas. We're going to clamp onto it, right? We're going to clamp onto it. We're going to cut it open, and then we're going to refuel it. Engineering is all about solving problems. Here's the problem. Satellites are running out of fuel. That's a lot of money wasted and a lot of research that we will lose if we don't continue to use these satellites. So why don't we? Why don't we fix them in space? Now, this just looks like an artist rendition. Them cutting open this multi-layer installation, them using these robotic arms. I know it just looks like an artist rendition. I want to show you more of the real thing. This is, and let me turn this volume down. This is the actual, this is an actual mock-up of this satellite at NASA Goddard Space Flight Center. This is a real flight robotic arm that will be used in space It has some cameras that are surveying this ring, that are surveying this target before it's going to actually clamp onto it. This the real deal right here is at NASA Goddard Space Flight Center. And that's what we do with engineering. We come up with these renditions to come up with a concept, and then we come up with these test beds, different ways that we're going to test these systems before they actually go in space. And you can see it's modeling the pushing and the grabbing onto the satellite. You can see we have this satellite on pneumatic systems to move it around to model that the satellite is moving in space. It's not sitting there waiting on us. It's moving at thousands of miles per hour. That's all about in-space servicing. And right, this you see me, the satellite just came to NASA about 4 months ago. I was so excited. Looks like a present, done it, doesn't it? We unwrapped that present, and this is how it looks unwrapped. We are going to integrate this huge servicing payload to it in 2 to 3 weeks. And you can see we have engineers, technologists from all over the place supporting this. It's just so great. So that's all about me, but let's talk about the lab. We're going to go through a little bit of the history. How did we get here with space? How did we get here? We're going to talk about launch vehicles. We're going to talk about payloads, building and testing, all that great jazz, right? We're going to have a great lab. I got one more engagement question for you. Before we jump in, what comes to your mind when you think of space? What questions do you have? If you had to choose any of these questions, what would it be? What are some questions you have about space? Yeah, that's what I've always wanted to know, if aliens are out there. I mean, come on, man. Time travel. Yes, yes. That's great stuff. Can we live or exist on other planets? Man, oh man, Monica, they are killing it with these questions. This is great stuff, man. Maybe Betsy will answer some of these for you. Does the universe end? Is it expanding? This question actually came from one of our high schools today that are interested in that came to this lab. How old is this? Is nice. I can see, are we alone is the number one question. I've had similar questions. Are we alone in this universe? Are we alone? Are there other beings? The universe is so vast, it's ever expanding. There's multiple galaxies. Are there multiple universes? Are we alone? Is time travel possible? If we want to figure out if we're alone, we may need to travel, perform time travel. We may need to travel at the speed of light. And then finally, what if something happens to this planet, right? Or what if we populate this planet in such a way that it's full? Is there somewhere else that we could live? Are there other planets that can support life? Huge, huge, huge question. We're going to talk about all of that today. But before we jump into it, what type of engineer does aerospace engineering? That's a question that came from Comic High School. Hopefully I pronounced that correctly. And New York Live. Well, it's an aerospace engineer. That's where I got my bachelor's. And an aerospace engineer combines just everything that has to do with these devices and systems in our atmosphere and beyond our atmosphere. That's the aeronautical within and the astronautical beyond. If I had to give you an example, the James Webb Space Telescope, we launched that a couple years ago. It's really breaking things that we know as engineers and scientists about the universe. It's answering questions and it's breaking theories, which we love about science. But the aeronautical engineer, he or she or they develop the rocket, right? They develop the rocket that will go into space, right? That's the aeronautical part. But then once once the satellite is in space, there were these astronautical engineers who developed the actual Webb telescope and the mechanisms that helped it unfold. It had to fit within the fairing of this rocket. That's an example of these two. All right. So let's talk about the past and the present and where we want to go in the future. It all started with Sputnik. This is the first human-made object. It's just about, how large do you all think Sputnik is? You can type that in the chat. Very small satellite, started the space age. Then after that, Soviets got their hands on placing the first man in space. His name was Yuri. And since they placed the first man in space, the United States was like, hey, we got to compete with that. They developed the Saturn V rocket. to allow, which weighs about 6.2 million pounds and has taken 24 people to the moon. That's the space race. That's the actual competition. And then once we learned that we can take people into space, we wanted to get better and better at it. So they developed the shuttle, Space Shuttle Columbia, which is like having a lab that you may have in your school, but having that lab in space. We use that because we used to work on the Hubble Space Telescope, and 27 missions to space have occurred on the Space Shuttle Columbia. And then finally, we figured that, hey, we got to start actually having rockets where we can reuse it. We would, launch these rockets, they come down to the ocean. Most of the parts weren't reusable, but nice private industry, SpaceX developed a rocket that for the most part, we can use most of it over and over and over again. That means even more science, even more astronauts could actually go into space, which I think is really, really cool. But none of that is as cool as what you're going to do. Unbelievable. One of you that is on this call in high school could be the first person on Mars. We got robots on Mars, but not people. It's mind blowing. I can't wait to see what you all do with your ingenuity, and you're going to get a chance to practice that in this lab. So what would you like to investigate? What are some things you'd like to investigate? Well, things that we investigate are, how do we communicate in space? We investigate astrophysics. How large is the universe? How fast is it growing? How long has it been out there? We care about our planet, right? The crazy power of the sun, that solar radiation, it could knock out our life if we weren't protected by our atmosphere, which I'm going to talk about later. So we want to protect this. We can predict weather by having satellites in space, right? So these are a lot of different things between space weather monitoring and environmental science that you can investigate. And then my favorite, obviously, OSAM. It's my project, OSAM. It almost ended the project because money, cost, and schedule matter as well. But we are still fighting. We're still rolling, man. Constance, we're still rolling. And I think OSAM will be coming to a theater near you in 2026. So now it's all about the payload, right? Let's talk about that, the components of it. The payload. The payload is whatever you take to space. It could be you, it could be the James Webb, it could be the robots, the helicopters that we've taken to Mars. That's the payload, right? Also, but it constraints. We talked about that. Like with OSAM, you got to be able to design this thing. And just like your project, you're going to make this balloon rocket system, which is going to be so crazy cool, but you only got a certain amount of time. You only got certain materials because materials cost, and you got to reach an objective. Your objective is to take as many, the greatest mass of payloads or paper clips up to the ceiling and keep it there as long as you can. That's what, engineering has objectives and constraints. That's important as well. Here, I'm just showing you different types of payloads. You got your spacecraft, you got like Hubble, you got the ISS, which the astronaut today I'm sure she's going to talk about the ISS some, and you got Apollo, right? These are different spacecraft. Now, you all, I don't know if I have anybody that can type in the chat. How do we get these payloads into space? How do we get these payloads into space? I love that concept. OSAM-1 is here to stay. Are you thinking about that? How do we get them? Yeah. Oh, thank you, Monica. Teachers, get to your keyboards. Yeah, teachers, if you could convey the answers from these students to us, engage a little, that would be outstanding. How do we get, yeah, SOAR. That's a cool name. It's all about the rockets. It's all about the rockets. Let me show you a sample rocket video here.
15 seconds. Guidance is internal.
Yeah.
12.
Thank you,
11,
Preston High
10,
School. Great
9.
job. Thank you, SOAR.
Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Power clear.
Wow.
minutes, 30 seconds.
Wow. I mean, you have to, when you see them looking at this rocket, it's not just their hopes and dreams, but there's something inside of them because they're actually, the first group of astronauts launching into space. There's a little fear, there's a little unknown, that's happening right there. That rocket, that much power, that much hope, just it's absolutely breathtaking. I agree with you. I'm not going to show this video. That's a really good rocket launch as well. So now that you've seen that awesome, awesome rocket, you got to think about this. Like, what does it have to overcome? What is the rocket you're going to develop? What does it have to overcome to lift off? It is extremely hard for a rocket to take off vertically, vertically. So our atmosphere, it has to overcome the atmosphere. The atmosphere is the friction from all of the wind, right? Once it gets past this troposphere, which is really the craziest part of the atmosphere, then it's off to the stratosphere and the exosphere. But as it ascends, the temperatures are just really, really harsh, very, very, very cold, and very, very, very hot as you get closer and closer to space, based on whether you're in shadow or you're in front of direct proximity to the sun. There's all these different, and then space is a vacuum as well. There's so many different things that make it a challenge, which makes it so cool that we've been able to achieve this. And you do this through the development of a rocket, launching these rockets to space. I'm showing in this image kind of how rockets how they've evolved some, smaller rockets. But as we wanted to take more and more people into space, we wanted to take larger and larger spacecraft payloads to perform, this breathtaking science that's been performed. We have definitely had to develop larger rockets. And you can see this latest rocket and the size of it here, which is really, really huge, right? So now, but even though we have these very large rockets, it's a little confusing because you think, well, we have all of this space. We have a huge amount of space for our payloads, but we don't. This just here, the payload system, this is probably less than 10% of the volume and the mass of the satellite. That's all we have. It's so inefficient. And that's why for this project, your goal is to see how with the limited weight that you have in a rocket balloon, how can you take the most sizable and heavy payload you can up to the cell. That's what you want to develop. We want you to have, the best efficiency process. And maybe you start now, but maybe you become the next, I don't know, the next Elon Musk to develop the satellite the launch vehicle and the rocket that take us, beyond our solar system. That's what we need, beyond the solar system. All right. So in order to do that, you got to know a little bit about propulsion. And there's two different types. One, there's the solid rocket. And I think of the solid rocket kind of like if you ever had a bottle rocket, like me and my brother, on 4th of July, we would launch bottle rockets at each other, which is probably not good. But it's like this instantaneous, automatic energy. Thing just launches super fast, but you can't control it. There's no control. It's very powerful, but you can't control it. Then you got these liquid rocket engines. And what's nice about those is that you can throttle it. You can control it in a way that you can slow it down, you can stop it. That's what's great about it. You have these options, right, for your rocket. The rocket you're going to develop, it's possible that you can develop it in a way that you can throttle it a little bit. And all of this is occurring because of Newton's third law, which says every action has an equal and opposite reaction. It's the conservation of momentum. As this pressure builds up in the rocket, the reaction is the exhaust gas goes in one direction and the rocket goes in the absolute other direction. Great question. Okay. So now we're finally at the point we're going to talk a little bit about your design, and I'm excited about this. You got all of these different pieces that you have. You have all these different pieces that we've given you, and I'm showing you a little bit of that here, right? When you open up this kit, you got this is going to be the pump so that you can effectively place the air in all of these balloons. The balloons, these are your propulsion system. And we've given you different kinds of balloons, even ones that are like extremely large and some that are much smaller because we want you to develop the system that's optimal for your design, right? We have some rubber bands. Why do you think we have rubber bands? You need a way to clamp um, your launch system, which you're going to attach this straw to your balloon. And also we've given you here some fishing lines. The fishing line is going to go from the top of the ceiling to the floor. And you need a way to attach the straw. The straw is going to go along the fishing line, and you're going to tape or rubber band the straw to the actual balloon. But you have to do it in a way that regardless of whether the balloon is inflated or deflated, the straw or multiple straws have to stay attached to the balloon. Now you're thinking, man, is that enough power? Well, that's why we gave you multiple balloons. We'll talk about this. You can utilize multiple balloons. Other things that you have in this kit is you have these paper clips, and this is important because your goal is to be able to launch as many paper clips as you can that are attached to your propulsion system up to the ceiling, right? And you're thinking, well, how do I attach them? That's where the engineering comes in. How will you attach them? What's your team's best idea? Maybe you try one idea and you fail, and then you try a different idea. Here's an idea though. We did give you a cup. So if you want to attach it using a cup, how would you attach a cup to your system? All right. I'm gonna stop giving you too many ideas, but these are all the different materials that you have. Can't wait to see what you're gonna work on. We even gave you some sandwich bags in case you want to place the paper clips in there. Fun stuff, right? So your goal is to construct a balloon powered rocket, and that launches your payload. That is the paper clips all the way to the ceiling. And maybe you have a single propulsion system. Maybe you have multiple propulsion systems, right? As you're thinking about this, though, I just gave you just a little bit, kind of spark your ideas, kind of spark your thought process. What do you think? What are you thinking are some challenges to designing this balloon rocket? Jump back in Slido. Hey, if you just jumped on, you can jump on the Slido and engage us. If you type in slido.com, that's the website, and those numbers 9011-264. That's going to give us an opportunity to engage you a little bit. Thank you, Monica, the hostess with the mostest. Yeah, I love these. I love this. Yeah, like how do I start? We're going to talk about that. That's one of the most important questions. Because if you don't start well, you may not end well. Come on, Constance. If you don't start well, you may not end well. So we're going to give you a cheat sheet for that. How do I obtain the greatest lift? Am I using multiple rockets? Is it about that? Or is it about reducing friction? Is it about that? What do I do if my rockets keep failing? Well, man, how do I release it? I'm glad you talked about that. In the kit, we gave you some clamps that you can use. We gave to support it. We also gave you some binder clips. So I'm glad you asked that. That is great question. But here is this cheat code right now. This is the cheat code. How do I start? You start with the engineering design process. This is the problem solving cheat code. I've used the engineering design process on every patent I've been able to obtain, every spacecraft development effort that I've led and managed. This is it. And this is the key. One, you start with the problem. Our problem is getting this rocket all the way to the ceiling. That's the purpose. How do we get the payload all the way to the ceiling? And before I just start taking my parts out and building, you want to do a little research. Maybe you research how to use balloons to develop the most thrust. Maybe you research on Google, rocket balloon designs. There's a lot of different things you can research. Then you design. And I'm saying, like, seriously, as a team, take out a paper, pen, pencil, or maybe Google Sketch, whatever you want to take out, and develop the design. How do all these parts come together? How do I assemble them? Which balloons am I going to use? How do I attach the straw to the balloon? How am I going to place the straws on that fishing line? Think about all of that. Do I add fins, right, to control some of the spinning on that rocket? You want to design it as much as you can, because if you design well, you're going to build well. If you think through it and design it on paper, it's going to be easier for you to build. And then you can see, we've given you like 9 balloons. You have the opportunity to fail and test and fail and test until finally you come up with the best design and you deploy it. And you deploy it. Maybe you'll get a patent for your design. I don't know. All right. So, I'm hoping that right now you're already thinking of some great ideas. You're already thinking of some innovations. You're already doing maybe a little research. That's great. Here's a couple little nuggets to get you started. One, think about fins. Think about how you're securing a payload, how you're securing the straw. Do you want multiple stages? Like, do you place these balloons in series for multiple stages, or do you place them all together, multiple balloons, to get the most thrust? And what other ideas you have? But this is important. You need at least 1 straw, maybe 2, that must be attached to the balloon to secure it to the fishing line, right? Or else you release the balloon, it's just going all over the place, right? We want it to go to the correct orbit, maybe that's the low Earth orbit. I don't know, right? And then you need at least 1 balloon, else you don't have any thrust, right? You need a balloon. You can't push it up. You need at least 1 balloon. And make sure it's secure, right? Thank you, Betsy. Make sure you have a good structure at the bottom, a good way of releasing it so it doesn't pop. And then that rocket design has to hold some mass. It has to hold some mass. All right. Very, very important. And Betsy has a great, a great idea. You can make a launch tower, right? That's how she did hers. And maybe she's going to show you an example of hers when we go into the breakout sessions. So now this is just different ideas that we've thrown in here, but don't forget to write it down. Anything you do that performs well or doesn't perform well, you write it down, because you want to remember as you're going through the process and you're developing this great rocket system, what worked, what didn't work, what do I need to place into this final design? So you got to document it. Engineers always have an engineering notebook, and we've given you a student interactive notebook where you can write down these ideas. You can take some pictures, you can add some videos. It's going to be great. And then the fins, people always ask about the fins. Placing the fins on the rocket may control how much it goes from side to side and it rotates. So think about that. All right. So then there's a question about staging. Staging essentially is like this multi-stage rocket. You may have a rocket that gets you halfway up up to the ceiling, then another rocket that gets you all the way up. It's challenging, but this is how we develop rockets now. We have these huge rockets on we have these huge propulsion tanks on a rocket that get us just off of the ground, the first kind of 60 seconds. Then we have other rockets that get us into space, and then we have another stage of rockets that actually, propel that satellite into its final orbit. So that's what staging is about. All right, so I want to show you just a quick video. This video is showing, one of our awesome interns. Look at her on the Notre Dame rocketry team. This is Katie, and she's building her own rocket, right? This is showing you, and that's a crazy rocket balloon there. That's huge. But she's showing you how she's strung together all of these different pieces, right? That's an example. That's an example. And you can see how she's attached her paper clips, right? You can see how she's attaching her straw. Great stuff. Man, she is kicking butt. I don't know how she's moving so fast. Man, she's killing it. Here's another video of some students actually launching their rocket. Hopefully this is sparking some ideas for you as well as they launch this rocket.
3, 10.
Not 3, 2.
I'm gonna fast forward just a little bit.
Bro, my brain. You wanna count?
4.
You wanna count?
Yang with me. 2.
Okay.
1.
Wow.
Oh man, he is psyched. One thing you can see is they used multiple fishing lines. Is that good? Is it bad? They used some very huge balloons. Good? Is that bad? That's you. That's the engineer. You're gonna investigate all of that, and I promise you'll come up with even something better than that. All right.
3,
So, um, we do have a couple extensions as well, and I'll end here before we wrap up. We do have an extension that if you finish this lab and you let us know you're interested, you can develop a stop rocket. And Betsy developed this great extension based on feedback from our teachers. So if you finish the lab and you send ET an email, it's possible that we can send you a stop rocket as well. And with that, I hope you are ready to blast off. Great engagement today. I am going to hand it over to Monica, the hostess with the mostest, to talk about next steps. Thank
Well,
you.
First we have to give Milton an amazing round of applause. That was an awesome introduction. I think
Oh,
I see
thanks.
students already have some balloons going in those classrooms in Miami Lakes and in Porter High School in Texas. They are ready to roll and get this design process started. We are going to get everybody into a breakout room so we can